Separating mixtures is an important concept to understand. Outside of your chemistry classroom, there are a lot of industries that depend entirely upon their ability to separate mixtures. For example, we now have a very thriving recycling business in our country. Also, when it comes to just handling our regular trash, there's a certain amount of separation of the trash occasionally that does occur before it goes to the landfill. Also, the mining industry. The mining industry spends a lot of time separating the mixtures that are dug out in the ground. They're called ores to extract the substances that have value. Now we're going to look at separating mixtures. It's kind of sort of some simpler point, but you will be responsible for understanding how 6 different techniques can be used. Now, the first important thing to understand is that separating mixtures, in order for a mixture to be separated, it's based on differences in physical properties of the substances in the mixture. Okay, so if everything in your mixture has similar physical properties, it's going to be very, very difficult, if not impossible, to separate it. Okay, so for example, if I had red and green ping pong balls, but I couldn't see that they were red and green, maybe I was red and green colorblind, or maybe I'm just plain old blind, and somebody said, here, we want to separate those. Say they feel the same, they weigh the same, they smell the same. There's nothing that I can figure out how to tell the difference between red and green. So that would make it very, very difficult for me to separate them. However, if I gave you a dumpster full of soccer balls and tennis balls and said we want to separate these, you could say, yeah, the soccer balls are larger, they're white, and they're hard. Tennis balls are fuzzy and smaller. And so you can see that more differences there are in physical properties, the more different that the substances are, the easier the separation is going to be. So we're going to start out by looking at 3 simple techniques. Now, why do I call these simple? Okay, because they require a little or no equipment to do the separation. Okay, the first of our techniques is the one that actually does require equipment, and that's magnetism. Okay, what do you need? It requires a magnet. So what has to be different? What's the differences in physical properties that are required? Okay, you must have a differences in magnetism. That's what has to exist in your mixture. Now, so that means that you have to have, you need a magnetic metal. Now, it's important that you understand that not all magnets are magnetic. You probably figured this out as a kid. Once you figured out the refrigerator magnet stuck to the refrigerator, you probably took one off and ran around the house sticking out on everything, trying to figure out what would the magnet stick to. And you discovered that most of the time it sticks to things that are metal, but not always. Okay, that's because not all metals are magnetic. Now, which metals are magnetic? And you're going to need to remember. Iron is a magnetic metal. Cobalt. Okay, nickel. Okay, nickel is somewhat. Okay, it's not very strongly magnetic. Okay, and metal steel. Now, what is steel? Steel is mostly iron. It's got a little bit of carbon mixed into it to give it more strength. Iron is very strong, but it's also very brittle. Steel is even stronger than iron. Okay, so if you have one of these substances in your mixture, then you can show. If you have a little magnet, a horseshoe magnet, whatever is magnetic will stick to the ends of the magnet. Whatever in your mixture is not magnetic will be left behind. One of the things that you're going to do for me is you're going to create a couple of what are called foldables, which are just simply the little flip books for you to help remember when do you use these different techniques and what type of substances could be separated using this. So if you're asked to give me an example of 2 things that could be separated using a magnet. One of these things has to be in your mixture, and then anything else would be separated. All right, let's go on to our next technique. Our next simple technique is density. To do here, We're going to use it density using water. Okay, so what has to be different? Okay, we have to have, obviously, this one's kind of like magnetism, differences in density. Okay, so you have to have one thing that floats and one thing that sinks in water. Now, the density of water is always 1. Okay? Water, if you take 1 milliliter of water, it weighs exactly 1 gram. And the units for density are grams per milliliter, or G over ml. So that means that the density of water is always 1. So if you have a substance with a density that's larger than water, meaning greater than 1, when you place it in water, it will sink. Now, the greater it is than 1, the farther down it'll sink. Okay? So if it's pretty close to 1, it'll just sink kind of low in the water, but it won't go all the way down to the bottom. Now, if you have anything that has a density of less than 1, it will float. Okay? And the farther, okay, the more less it is than 1, the farther it'll float. So something like styrofoam, which has a very, very, very low density, will like float right on the very, very top of the water, while something that's cork will float kind of partway in the water. And you'll find there's other different plastics that may actually kind of go down into the water partway, and then they'll just stay there. They won't sink all the way to the bottom, but they won't float on the top. So the closer your density is to 1, okay, the farther down it's going to sink into the water. Okay, so for example, you have to have something like, if you put like cork, plastic. These are things that when we put them, oops, sorry. Okay, if we have the mixture and then we add water to the mixture, you get one of your substances, hopefully, to float, either on the surface or farther down, okay, and then whatever else you have left behind, okay, will stay on the bottom. Okay. That's the point of using, that's what density separation looks like. Okay, you have your mixture, you add water, and the lighter things that float to the top, and the heavier things just stay on the bottom. That's a good density separation. So you'd have one thing in your thing has to float, and one part of your mixture has to be heavy enough that it will sink or stay sunk in water. Okay, next one. That's simple. Solubility. You need water for this too. Okay? You don't always have to have exactly water. You have to have water or something that's called solvent. Solvent is any substance that can dissolve something else. Water is the most common solvent on Earth. A lot of things dissolve in water. Some things don't dissolve in water, but they'll dissolve in other things. Like some things will dissolve in alcohol that don't dissolve in water. Like if you have a Sharpie, okay, the reason we use Sharpies is because if things get wet, the ink doesn't run. However, if you get alcohol on a Sharpie pen, the ink will run just like it would like other ink pens do in water, because Sharpie ink dissolves in alcohol. Alcohol is the solvent for the Sharpie ink. So you have to pick very carefully what your solvent is going to be. Okay, so what this means is there has to be, obviously, differences in solubility between the substances in your mixture. Okay, that means that one thing dissolves, okay, and one thing stays solid. Okay, now it's important that you understand that the dissolving process, students tend to not understand what does it mean when something dissolves. Remember we said when things are solid that they're in a three-dimensional crystal structure. There's rows and columns. Okay, the more rows and columns, the larger the crystal. Okay, so if we look at something like a salt crystal or a sugar crystal, that's actually huge on the atomic scale. There's just millions and millions of rows and columns in there. However, when we put them in water, the water molecules have the ability to just take the crystal, the separate particles that make up the solid crystal away from each other. It basically just breaks the crystal down. Now, it doesn't melt them. However, they have very, very similar properties now to something that's been melted because they look like they're in a liquid form. However, the important thing for you to remember is that the stuff that's been dissolved has not been melted. Melting requires heat. To dissolve something requires a solvent, okay, which means that when things dissolve, they don't get hotter. So the extra energy to look like a liquid is coming from the particles, the liquid particles that are kind of giving them some of their kinetic energy, like the water, the solvent. Okay. But that's going to be really important when we talk about another technique a little bit later. Okay, so for example, things that dissolve very nicely in water, okay, so things like sugar, okay, salt, these types of things dissolve. So if you have something like sugar or salt mixed in with something that doesn't dissolve, okay, so you take your, this just means that you simply take your mixture, okay, and we're going to add water again or some solvent. I'll put solvent here because water can be solvent, but other things can be solvent too. Okay. So rather than having something that floats and something that sinks, okay, now our sugar and our salt are now in tiny pieces all over inside the water, okay, and our stuff that doesn't dissolve stays on the bottom. Okay, so look at the difference here. This is floating. This is now dispersed all through the water. Now what we can do is we can simply pour the solvent with the dissolved substance away from it, and then we can separate. So this substance will stay behind in the container. This gets poured off into a new container. Okay, so those are our three simple techniques: magnetism, density, and solubility. So there's a limited number of mixtures that we can separate using those. Let's look at some more complicated procedures. These are our complex procedures, okay, because they require equipment. Okay, our first one is filtration. Okay, what do you require? A filter. Remember, a filter is just a substance with holes in it. So what has to be different in physical property? Differences in size are required. Okay, so you have to have a filter that has holes that are small enough that one part of your mixture can't go through, but large enough that the other something else in your in your mixture can go through. And so this is a very special note. Does not work to separate dissolved substances from the solvent. The reason being we need differences in size. And a solid that's dissolved into a solvent like water. Now water is very, very, very tiny. Water goes through just about everything. Okay? So that's why, it's like water leakage is a big problem in a lot of different ways. Okay? We need substances like plastics and things like that, which don't allow water to penetrate through them, okay? Or metals, things like that. Okay, but if we want to have a filter that has holes that are small enough for water to go through, but not something that's dissolved in it, okay, that's really, really, really tough, because we can't really manufacture something with holes that are that incredibly small, okay, because water is one of the smallest molecules that are on the planet. It's only made up of 2 hydrogens and an oxygen atom, so it's incredibly small. Okay, however, even though something like sugar is a lot larger than a water molecule, okay, we just simply can't manufacture something that has holes that are small enough to distinguish between sugar and water. There's different things, better technique that we can use to separate something that's dissolved from itself. Okay, however, okay, so let's say you just have, we have something that's small particles. Okay, and then we have larger particles. Okay, and the particles can be anything. You just look at it and you ask yourself, which one is there a pretty good difference in size between the two? Okay, and so what you do then is you pass the substance through a filter. This is going to be my filter. It's going to look like mesh, okay, like cross-hatched. Okay? And so remember, we said the small particles fall through, and the large particles get trapped and they stay on the filter. Okay, so that's how filtration works. Okay, the next one is called distillation. This is what you do want to use. Okay? This requires two things. This requires heat, okay, and a way to catch vapor. Vapor is just a gas, if you want the vapor. All right. Distillation is really good if there's differences in boiling points. Not everything boils at the same temperature as water does. Some things boil off much faster, some things take a lot more heat before they boil. So if you have a mixture of liquids, you can separate them using distillation. Or, okay, this works really good for separating dissolved substances from the solvent. Remember we said filtration doesn't work very well? Distillation does a great job. Okay, so let's look at, okay, so here we have something with low boiling point and something with a high boiling point, okay? So like, oops, sorry about that. Alcohol. Alcohol boils at a much lower temperature than water. This is actually how they make alcoholic beverages, okay? Because usually at some stage in the alcoholic beverage making process, we use bacteria to actually create the alcohol. And the bacteria create it from sugars and starches and things. So they break down a lot of like grain products. And then that's kind of messy though. And so what we want to do is we want to distill off as much of the alcohol away. That's what we actually put. Now it's not pure. Okay? When you do the distillation process in like distilleries and breweries, they don't completely distill just alcohol, so there's no water in it. Otherwise, people would die when they drink alcoholic beverages, because drinking pure alcohol can actually kill you. So what you're drinking when you go to the store and you get beer or wine or some type of a beverage, it's actually a mixture of alcohol and other things. And wine isn't distilled or purified at all. Okay, that's why you get kind of that nasty sediment that floats down to the bottom after a while. Okay, but drinks like vodka and gin and whiskey and everything are distilled. Okay, so they contain a high amount of alcohol compared to the rest of the mixture. All right, so how does that work? So what you have to do is you have to remember I told you need heat. Okay, so here's our container. Okay, and it's going to be fire. Okay, so I'm going to heat my mixture. Okay, and I'm going to put a little thermometer in there because I have to monitor temperature very, very carefully. Okay, so this is a thermometer. Okay, and then as it starts to heat, the low boiling point substance, okay, starts to escape the container. Now, if I want to actually capture the vapor, like when you're distilling, the stuff that's coming off here, that's the stuff you want to capture. When you set up your distilling apparatus here, okay, you put it underneath. If you see in the labs, a lot of times you'll see people are boiling it, and it's actually in a flask that has a cork in the top of it, and so the vapor can't escape. A distillery, usually uses something, a really crude one, uses something like a big funnel suspended over the top of the container. So as the whatever it is that you want rises, okay, and then you simply attach this to like a coil. Okay, and as it travels to the coil, it cools down, okay, and then you put this over their container, okay, and what you get out the other end, okay, is the vapor cools down and becomes a liquid. So you get your stuff, you get your liquid back. So you basically heat it from liquid to gas, and then you cool it back down to a liquid. Okay, but the important thing is that what you do is you leave behind your higher boiling point substance, most of it. Okay, distilling isn't going to be 100% pure. You're still going to get a little bit of your high boiling point mixture. Okay, you can distill things over and over, and eventually get it pretty pure. It's not perfect, but it works pretty well. So the reason we say it's really good for separating dissolved substances, because the solid that's dissolved in there is still at its solid phase, and it would still require energy to melt. So as the solvent boils off, the solid gets left behind. This is why if you leave a pan of water on the stove, like you're going to make spaghetti or something, and you walk away from it, you come back and the water starts to boil down because you forgot, and you usually get you get white stuff on the inside of your pan. Those are the substances that are dissolved in your tap water. Okay, that's the stuff sometimes people say it makes our water hard. We say it's got hard water. So the harder your water, the more stuff you're going to see dissolved in your pan. Left in your pan as the water evaporates. All right, the last one is the most complicated one. It's called chromatography. Okay, chromatography, okay, requires a paper, if you're doing paper chromatography, okay, or, okay, a very fancy machine called a gas chromatograph. Now this is a very large and expensive machine, okay, because what it does, a gas chromatograph, is it vaporizes a solid sample. So it zaps it with a laser and makes it a gas. That's what's called a gas chromatograph. Paper is used for separating liquids. Now, what you have to have, this one also separates, you need to have differences, it separates based on size. This is not quite like a filter though. Okay. In chromatography, you have to have, the substance has to be pushed across either paper or pushed through air. Okay, and just like if you lined up the entire football team at all in their football gear and everything on the starting line at the track, and you said, okay, I want everybody to run around as fast as you can, you notice that the big, heavy linemen would probably not run as fast. Okay, and then your tight ends and your running backs and probably your quarterback would run a little faster because they're probably smaller people than your linemen. It's the same thing with chromatography. If you have things where the particles are small, as they get pushed, it's easier to push them, so they end up going in the front. They end up moving faster, and the larger heavy particles are harder to push along, so they end up slowing. So let's look at paper chromatography. So this is really good for like inks and paints. You can separate out the colors because the colors in inks and paints, called pigments, are usually different sized particles. All right, so let's look at paper chromatography. Okay, so I'm going to take a piece of paper, okay, and I'm going to put my ink on the end. Okay, so here's my ink. I'm going to put a little bit of ink here down there on the end. Okay, and then I'm going to take it and I'm going to put it like this down into a piece of paper, into some, okay, like this, okay, and I'm going to put it in some water, okay, and the water's going to be right here, okay. Now what happens is the water moves up the paper, and the water does the pushing. So as the water hits the ink, it starts to push all the ink particles along. Now the lighter weight particles, let's say red was very, very light. After a while, the red particles start to make a line up here because they don't weigh very much, so water pushes them faster. And let's say then there's some blue, okay, that gets left behind. Okay, so the red is lighter and the blue is heavier. Okay, so as it pushes along, the red gets to the top first, and the blue comes along slower. This is what I mean by chromatography. Okay, the word chromatography means to color right, or color image, and that's kind of what you get. You get separation of colors. A gas chromatograph does something kind of similar, except it doesn't have paper and water. It just zaps the substance with a laser, and then the particles that are lightweight move through the air faster. Okay? They usually have like a little bit of a stream of air moving through the chromatograph above the laser. So as the vaporized things rise up, a stream of air pushes them along. The lighter weight things go into what's called a detector first, and the heavier things come second. So the chromatograph has to be attached to a detector, and the detector has ways of determining what's the identity of the substance. So this is the chromatograph is really, really helpful, a gas chromatograph, in a lot of forensic applications, because the question is, oh, I have this mysterious stuff on the dead guy's shirt. What is it? You can take it to a gas chromatograph, and you can take a little sample, and it will actually separate out the particles and tell you what the particles are. And then people that are chemists kind of know, no, those compounds are commonly found in this particular substance, so they can identify what it is. So that's why a lot of forensic, if you want to work in forensic science, you have to know a lot about chemistry. All right, so I'm going to give you a chance to kind of mess around a little bit with this. You kind of have to be creative and think about what your knowledge tells you about two things that you could separate through each of those. And for your quiz, you're going to have to come up with a mixture, or at least two different kinds of things that you could separate using a couple of these different techniques. Good luck.